Right guys, different tack, completely different sort of presentation this one. It's technical, and there's not any pretty pictures, apart from this one. Ta-da! It's not bad. Yeah.
Very happy man.
Yeah. So I call it How the Theory of Relativity is Useful to Games. On the invite, it was why it's needed in games, so I've taken a bit of a step back just to why it's useful. It's a bit easier to defend. All right. So almost all games have got some sort of spatial data structure, and I'm representing it in this little graph here. I'm just looking at one dimension of the data structure, and for simplicity, let's just say that we've got a grid for your world. So in one dimension, that's the horizontal axis is your grid, and I've got time as a vertical axis here. And what you're seeing up here is the bottom set of cells is your current state. The content of all the objects in your game are in the set of cells on the bottom, and the next level up is your next frame. So you're advancing one frame, you've got to calculate what is going to be the state of your world in the next frame. And you can't see it very well, but there's a couple of little blue lines there which are just saying that in most games, when you're updating the state, you need to find out all the interactions that happen between nearby neighbors. So usually you want to find out what interactions are happening in the same cell, the current cell, and the neighboring cells. And so that's what this little set of arrows are for. So that's generally how you break up your world into smaller chunks. There are two problems with this basic method of updating a game world. The first is that, your computation cost increases with the size of the world, and the real world doesn't have any actual bounds, so you've got a problem, which is that unbounded world, it's going to take infinite time to even do one frame. So here's an idea. Instead of using a grid, we use an oct tree or some sort of hierarchical structure, and you work out where the camera is or where the player is, and as you look at parts of the world that are further away from the camera, you use much bigger grid cells, so you have a lower resolution. Let's say you have a certain number of objects per grid cell. Further away, you have bigger grid cells. It takes a lot less time. In this example, I think I'm just showing sort of 3 of one size, and I double the grid cell size, and the further away you go, the bigger the cells are. The problem with this is, well, it still takes infinite time if you've got an unbounded world, so it's not much of an improvement. So the solution is, a pretty good solution, is you want to actually increase your granularity in time as well as in space. So as you go further out and your grid cells get bigger and your resolution of your objects gets less, you also want the time resolution to be less. So what I mean by that is that every time you you do your update step, the things far away, you may only be updating it every 8th time, and the things twice as far away, you might only be updating every 16th frame, and so on and so forth, which looks a little bit like this. So you can imagine that these tiny little inner boxes are updating all the time. They're close by, they matter a lot, and the objects that are far away, generally big things that are far away, you don't care that every leg of the ants a kilometre away is updating properly, right? You've got mountains and you've got planets a long way away that just update in a very simple fashion. So it's kind of okay that to do this level of detail, which I guess you could call it a four-dimensional level of detail, because you've got less detail in all your three space axes and in your time axis. And the nice thing about this is it's finite, so that's good. You don't need to have a bounded world. You don't need to have brick walls around your world and to still have it feasible to compute. It still takes up infinite memory, but I'm going to claim to you that that's not a bad thing, because if you think about it in a simple sense, you're adding on. I haven't got a laser pointer. Do I have a laser pointer? No, I don't. You see in this diagram, you've got 3 cells at 1 meter in size, then you've got another 3 cells that are 2 meters, another 3 cells that are 8 meters, another 3 cells that are 16 meters in size. If you keep on going, you have got an infinite amount of memory that you need to store all the objects. It is an infinite world. But it's not necessarily a problem, because if you think about it, all this memory that's being taken up with objects a long way away is only being updated very slowly. So what you have is as the memory goes up, the latency required goes up as well. So this is kind of a manageable thing in most modern applications, because you've got a lot of very fast-changing memory, you've got a small amount of fast-changing memory, which you could have on the cache, for example. You've got memory that might only need updating a couple of times a second, which might be on your hard disk, and you've got memory that only requires updating every 10 seconds, which might be a call over to the cloud, etc., etc. So it's a kind of manageable thing. That the problem is not the amount of memory, it's the latency. If you're able to have a big enough latency, then you can store a lot on the cloud. Anyway, I'm sort of getting off topic a bit. The other problem with this system at the top is I drew these little blue arrows to say you're interested in the interactions happening locally, but the problem is, if you don't know what the maximum speed is of objects that can be in the game, then you don't know how many neighbors that you need to check, because in the space of one frame or one update, an object could have moved from one cell into the next cell long. So we're checking 3 cells in this example, but if the maximum speed that objects can go is bigger, then you've got to check more cells. And so the computation in any game is going to grow if the maximum speed an object can have is bigger. So you've got a kind of equivalent problem, which is that if you've got an unbounded speed of objects, then again, it's going to take an infinite amount of processing to actually accurately update your world, because you don't know in one frame's time if a meteorite going 1 million miles an hour is going to come and hit my hand. You've got to check the entire world. So it's a problem that people kind of gloss over in games, because they just give objects a maximum velocity. So what I'm going to explain now is why it's not a very good solution to just limit velocities to a maximum. So this is kind of the nuts and bolts of this talk. This diagram here, we've got an imaginary situation that you've got a space station and a spaceship is going to leave a space station. If we're someone sitting in the space station, we kind of think of ourselves as being stationary in our space station. And in this diagram, the ship is moving off pretty close to the maximum speed that we've decided to clamp all of our speeds to. So hopefully you can sort of see that in the graph. I don't know, does that make sense? So from the perspective of the person on the space station, they're not moving, so that black line is vertical. And they see the ship as moving off, as you can see in the green line, the green vector. So if we take that situation, because we can't really say that it's right that the space station is actually at a speed of 0, because it depends what you're relating it to. Relative to itself at 0, yeah. So from the perspective of the ship, it looks like this. So if you're someone standing on the ship, and you kind of think, well, I'm not moving on this ship, you see the space station as having moved off in the opposite direction at the same relative angle. The problem is that now your maximum speed has also shifted, your clamps have also shifted. So you're standing on the ship of this spaceship, and you're in a situation where possibly you can walk in this direction, but you can't run, but you can run in the other direction. Or if you throw a ball in that direction, you can't throw it faster than a certain speed, but you can throw it as fast as you like in that direction. I mean, it gets even more ridiculous the closer you get to that limit, where you get to a point where you can't move your hand that way, but you can the other way. And it's just not really very workable, because the physics of your game is supposed to operate at any speed. It shouldn't have a specific place where you just can't go beyond. So this is where Einstein comes to help us, because there is a speed limit in the world. It's the speed of light, and we can use the kind of the maths of that to help us in games. So in Einstein's world, this is actually what happens. So we've had a top diagram, and from the top diagram, the one below, we've sort of transformed it to the ship space. Well, this is actually not the case. In the theory of relativity, it tells us that if the red line is the speed of light, so for this very fast speeds, it actually looks like this bottom diagram. And the transform is the difference between the middle diagram, which is a shear. You've sheared your graph of space and time, to the bottom diagram, which what's actually happened, if you imagine the top one as sort of being a box, if it's symmetric in time, is you've stretched it along the two diagonal corners and compressed it along the two other diagonal corners, such that the area of the box is the same. So that is how you go from one person's perspective velocity to another in relativity. So it's quite a simple idea. It's a completely linear transformation. And what you see is, so we're going from the top box here to the bottom box here. We've made a sort of diagonal stretch and squeeze. And so from the perspective of the person on the spaceship, you're stationary relative to yourself. So it's a vertical line, but your maximum speed is still the same distance on both sides. So it's a kind of interesting type of transform. And it's absolutely true of the speed of light. So the speed of light's going 300 million meters per second. If I travel at 200 million meters per second, then the speed of light is still 300 million meters per second faster than me, which is a bit strange, but that's an example of why it is. So the angle of these maximum speeds does not change depending on your speed.
Transforming the problem effectively into like a precision problem or something. As you approach this maximum speed, you're shearing it such that relatively they're the same, but I suppose from a precision point of view, in terms of numeric precision. Yeah,
you could, and I'll come to that in the next slide, because basically this is about having to regenerate your grid as you go, effectively to get around that precision problem, I suppose. Okay, all right, so, well, there's only one more slide. So let's take this idea. We don't have to use the speed of light, it's very fast. If we...
It's a lot slower in other mediums.
True, and in the medium of games, we can make it a lot slower, right? So 300 million meters per second, divide that by a million, 300 meters per second is still faster than a bullet, so maybe it'll be a bit less realistic. You'll have some strange time-bending effects, but it's okay.
Light can be as slow as 30 meters a second.
Okay. That's Isaac Newton's transform, and this is Albert Einstein. So let's put a grid on it. So it's kind of the same thing as we had before with a grid, but in this case, you've got a maximum velocity you can go at, so you don't have this problem of how many cells you need to look at. And so if we do the same change, so if we were at the space station, and now the ship has left the space station, so the second one down, what we do is we take our grid and we squeeze it and stretch it just the same way as the previous slide. And now our ship is taken off from the space station, and that's what our spatial data structure looks like. It's a bit uneven, so what you then do is you regenerate it, which is, in this case, it's quite easy. One has doubled in its resolution, the other one's halved, so it's just a case of merging some cells together and dividing some cells, and then you end up with a uniform data structure again. So whatever speed you're going at, your data structure has to alter to reflect it, and that means that your data structure is not tied to a specific velocity, which is a big difference than most games. And we can do the equivalent with our level of detail system we had right at the start. So same thing, which is all great. There's one problem with the whole thing, which is that I've only showed you one dimension of space here. When you get to 2 and 3 dimensions, it gets a lot harder. And this V shape in 2 dimensions plus time is a cone, and in 3 dimensions plus time, it's a hypercone or a light cone. And there's no rigid data structure like this, like a grid or an octree that fits. So you need to do something more complicated, like probably a Delaunay triangulation, which is not as scary as it looks. The purple thing is Delaunay triangulation. The blue thing is the what's it called? The Voronoi cells. So the blue cells become your equivalent of the square octrees grid cells, and then you have to do a similar split and merge process, but I haven't got time. And then you have a hierarchical equivalent, which is kind of like the top one above, because you need to have this hierarchy so things are less detailed in the distance. And those things are called Voronoi tree maps. So I haven't experimented with it, but that's it.
Usually in churches.
So if anyone's interested in exploring this area, then let me know, because it's kind of an interesting subject area. And to conclude, you can get an infinite world size, an infinite subjective speed for a person with finite computation and finite storage recall per second, but it doesn't work in multiplayer. You get some time synchronization problems.
I was going to say, you also subtly glossed over the issue of the entire thing requiring an algorithm that's invariant under time and spatial update zone changes as well. So in other words,
No.
an algorithm that gives you the same results if you do it in small steps as it does when you do one big step, and the same for space as well. And that's a exceptionally difficult problem in computing science.
Well, no, not really. I mean, it's quite common of level of detail systems that you update less frequently to things that are further away.
For instance, the way most physics engines run for real-time games, if you change your time step, will give you different results.
Oh yeah, yeah.
Including the version that gives you the same results under different.
Yeah, you can't just plug in physX to something like this. Yeah, it's true. It's true. Yeah.
So the person's mass increases or something or other when they've gone past, and there's
Yeah.
an event horizon.
Yeah, event horizon is general relativity. This is just special relativity, so it's a lot simpler. The mass increase is all kind of this one at the bottom, it's all a consequence of this transform. Everything else sort of falls out from this transform.
The mathematics of that transform from shifting relativity from a ship to a station, you're skewing it and keeping the area the same.
Yeah.
How do you just calculate the speeds of both and then it pushes the rectangle over? Like how you've drawn your graphs up there. I take it those are 3 different frames of reference and somehow something remains constant.
They're 2 different frames of reference, right? The first one in bold is the station, space station's frame of reference, and the 2 below are 2 different versions using the spaceship as a frame of reference, right?
And what's changed between the 2? What's the coefficient? Or how do you
The top one is what Isaac Newton thinks.
Okay.
The bottom one is what Einstein thinks. And it's called a Lorentz transform. And that's just how it works for light.
Okay.
Yeah.
And what sort of game rules do you imagine, or is there any that come close to sort of implementing this sort of...
Most likely space, because the reason games get away with having bounded velocities and bounded worlds is because usually they're on the Earth.
Right.
But space is a much harder problem because you have a spaceship and all you need to do is fire thrusters for longer. There's no friction, so you're going to hit your maximum speed at some point. And you've got nothing in space which tells you what 0 velocity is. So where do you place your grid?
Yeah.
You know, you can place it sort of where the sun is.
What did the guy end up doing? He was making spore. He did the Sims first, and then he was trying to make that sort of concept real big, where you like create universes and stuff.
I don't think Spore did that, did he?
Spore's not that big.
David Brabham did with Elite and stuff like that.
Have you been talking to David Braben recently?
No.
Do you have an application for this?
Huh?
Do you have an application for this?
No, this is just a talk.
You're doing your spare time.
No, I read up on it before, and as far as I'm concerned, it's not that bit's not that difficult, right? That you stretch it that way instead of shearing it. And people think, whoa, yeah, but that's the fundamental of special relativity. That transform is what it's all about. So, anyway, if you're interested in doing something along those lines, then let me know. We'll make an interesting game.